those of you who don't know me, I'm Lee Erikson. I'm with the USGS, the Geological Survey. And when I first was putting this presentation together, I was, well, let me give you a little more background. So my background is in coastal engineering and research oceanography. And I look at climate change impacts. I've been looking at climate change for about 10 years now and its impact on the coast. Sediment transport modeling and erosion and wave dynamics and that sort of thing. So I'm basically a numerical modeler and I have a whole team that's helping out now. And when I was preparing this presentation, I was aiming to do, yes, coastal erosion, flooding, and shoreline protection and kind of a big overview. And I wanted to touch a little bit on nature-based solutions to structures for coastal protection as well. And I have very little experience in that. It's been like 15 years since I looked into that. So I contacted Chelsea because I was looking down the list here and I was looking at the audience and I saw Chelsea was on there. And so I asked him to join me in this too. And then we've communicated back and forth a little bit. But so it ended up being more or less a shameless plug of what we're up to that we can deliver as a product to the North Slope Borough to help you in implementing rather than just continuing research. Because I was rereading again the intent of this presentation. That was a big long intro. Sorry about that. We'll get right into it. So just going to talk a high-level overview of 3 points: existing and emerging protection measures, coastal erosion and community flooding across the North Slope Borough. Overview of that, and some past and anticipated changes in flood and erosion potentials and hazards. So the very first part, following up on Scott's presentation this morning, there's a bunch of shoreline protection measures across the North Slope. This is an image or a figure taken out of the Army Corps report in 2019. On some other images coming up here. This is Barrow and Wainwright back in 2009. I'll be curious to see how it looks these days. In September 2017, the HESCO baskets here, and this is a nice example of the beach eroding away and maybe notwithstanding the storm's cases so much. Nature-based solutions are another option that's being looked into, and my understanding is that Point Lay is kind of a pilot study site where they're looking into alternatives and potentials. Really fascinating as well. Beach scraping, berm protection during your storm events, dangerous, yeah, but serves its purpose temporarily, right? I can see how it's dangerous. So all through the North Slope Borough, there's all kinds of different geomorphic conditions. There's barrier islands, low elevation tundra, beaches, and permafrost bluffs. They all have different erosion patterns, processes, and mechanisms that happen to them. So talking about, and the flooding that goes along with it. Partial list of flooding events past that had happened in the past. It's very working on compiling this, working with the state on this as well. To give a big overview of the erosion that's been happening in the past across the North Slope Borough, this is a study that looks at the long-term shoreline change rates from the 1940s to the 2010s. This was done by my colleague Ann Gibbs, and takes a regional approach, systematic approach, looking at the whole area. And you can see here that the Beaufort Sea coast, right, on average is minus 1.7 meters per year overall. And this is now the sand and gravel beaches that we're looking at. Hotspot there from Cape Halkett to Point Barrow, basically. And to note also, right, that's the averaged rate, but there's very episodic areas, very high rates that happen. So it can be up to 10 to 18 meters in a year. On the Chukchi coast, it has traditionally been 0.2 meters per year, so much lower rate on average. Barrier islands, also an important part across the North Slope. And I would say that they're quite important, maybe not for the infrastructure directly, except for those communities that are on the barrier islands, but they also provide protection from direct wave attack to the main coast, right? And the study that we just did pretty recently shows these migration rates to be pretty strong, and they're mostly migrating westward. Many of them, they're dynamic, they don't remain intact throughout, but they go in and out, but they are moving quickly. Also, bluffs, there's been a lot of work, and we've done a lot of work on permafrost bluff erosion. Picture on the bottom left is from here, Utiqiagvik and Erikson on the upper right-hand panel, where we have a very nice data set that's high temporal scale as well. And in going and looking very closely at those high temporal resolution ones, it's also very clear that there's an accelerated rate. You can see the blue line, it's 1950 to 75 averaged, and then it keeps going down. So the vertical axis here is the retreat rate. And the red line is this last 2 decades, 2000. Obviously, there's a spatial variation along the bluff, but you can see that there's acceleration happening in time, with time. And that acceleration, i.e. the increases in the rates of the erosion, can be attributed to the warming climate. There's been quite a bit of studies now, and it's pretty clear that it's the multitude. You have the sea ice declining, which causes the larger fetch, which also now is not coming back until very later in the fall. So you have more storms that can hit. And then we have the subsidence of the permafrost, and we have just thaw and slumping of the bluffs, et cetera, et cetera. This figure here on the bottom left is a model that was trained with historical data and then run forward in time. So up to 1980 to 2070, and it's the relative contributions of the thermal erosional components. So the sea surface temperature and the air temperatures that are causing sloughing, and longshore transport, cross-shore transport, and sea level rise. And sea level rise is pretty negligible in the overall picture of it. Thermo-erosional, very prominent along sections of that bluff. This is again Utiqiagvik, Barter Island Bluff, and then other sections, it's the cross-shore and the longshore sediment transport driven by the waves. So it is a variable thing, right? A recent study by David Nielsen was a nice recent one, where he's looking into the future. He took the circumarctic approach, so a larger scale, and trying to get an estimate of what does the future hold as far as the erosion patterns go. And you can see, so this is a regional scale, right? So it's a little coarse, it's very coarse. We're up here, and this is the observed erosion based on the ACD database. And these are modeled going forward in time. This is the historical, which is meant to repeat the observed, but there's always a bias in these climate models. When we look at the changes with the different scenarios, so 2.6 is a low climate scenario, 4.5, and 8.5 is a higher emissions scenario. And you can see the gets hot and blue, hot colors there. So our area here is anticipated to be continuing erosion. But that was again a larger scale modeling approach. We're very concerned also about trying to ascertain what the future holds, both from the erosion perspective and the flooding perspective. But we want to take a more closer, detailed look. So we've been running a bunch of global scale climate models, which account for the patterns across the whole globe, and then downscaling them to regional level, down to Alaska, and then taking that and taking it further down to the very local level. So it's a systems approach, going from global to regional to local scale. And we're using the latest, the CMIP6, they're called, the 6th generation, and the highest resolution that's available thus far in the climate science. And because there's a lot of bias and variances in the climate projections, we run as many as we can, and we managed to run 7 so far, and it's taken about 2 years. And now we're at a point where we can synthesize that data and bring it really to the local level. This is another way of looking at this modeling system, just another graphic for it. So global to regional scale, near shore waves, storm surge modeling. So we're looking also at the water levels, not just the waves. And we're taking that information into high resolution models, which are overland models. And for that, we need very detailed high resolution digital elevation models. So we get that accuracy in there. And 3 minutes in, we're running lots of scenarios for the different future storms, not the past storms, but the future storms, and in combination with different sea level rise. And this is partially funded by the CASC, Climate Adaptation Science Center, and we're doing a pilot work right now with Elam, Unalakleet, and Utiqiagvik is our third community. And so let me speed it up a little bit here. So here is just a timeline, 1979 to 2050 examples, and you can see this is outside of Utiqiagvik. You can see does show the trend in increasing in wave run up. It is showing up. Down here is a map, but you can't see it. That is unfortunate. Anyway, it's been on every slide. Here, what my point here was to show that in these models that we're looking at closely now, we're here looking at the wave run up, anticipated wave run up, and it's by decade, so 79 to 1990, 91 to 2000, and so on up to 2050. And the red colors is the later. And what you can see is that there's always the hump in all these locations across the North Slope Barrow tends to go to the right. So we're getting more maximum wave run up all into the fall season. And that's because of the sea ice not coming back. And we have basically unlimited fetch as well. And that corresponds with the opening of the sea ice. This is here a sea ice concentration. And we see that story across Point Lay, Wainwright, Utiqiagvik, Prudhoe Bay. This is not for prime time at all. We're just testing the model that we have, overland flood model of Utiqiagvik. Here we put in a 2.5 meter storm surge of 2 meters and 2 meters sea level rise. And this is what we've ended up with so far. Just very prelim. And what we're showing here is flooding depth and the storm erosion. So the erosion that happens with that particular storm. I'll give you an example more of Unalakleet, give you a little visual. So we're actually running the storms themselves in time steps, right? So we're really capturing overland flow, how it's connected. We do validation. So this is a validation against the Merbach conditions. These red triangles show where flooding occurred during this last September 2022 event. And I think the model did pretty well connected there. So that's one of our validation storms. And on the right-hand side, it's the exact same condition, but with 1.7 feet of sea level rise. So we can play these games, right, to see what's going to be what can happen in the future. Other products that come out of this are maximum water velocities, good for emergency hazards and planning, maximum wave heights during the storms, and as I said, the erosion, morphodynamic change that occurs during the storms. And a large component of this, while we're doing the modeling and bringing it down to the local scale, is we want to make sure to make products that are directly useful to the planners and managers. So we're trying to to work with all these stakeholders so that we can make an appropriate tool, map products, or whatever it is that might be needed. So this is a map product that was DGGS was involved with, an AUS and NOAA, National Weather Service, and the feedback that we're getting from stakeholders will be including these kinds of maps most likely. So we have all the infrastructure GIS layers overlaid, so we can see. This is another, we've been working on this in the lower 48 for many, many years. And this is the web tool that we have developed for the lower 48. So you can, as a planner or grant writer, that's the other thing that's we're aiming, is a tool that's easy for people to go in and do grant writing. So you don't have to spend money and time on this modeling, but instead just get them to do grant writing. So in here, and the user can just click on sea level rise and the storm that they're, and this is the future storm, and then you can get the flooding, and you can overlay different GIS layers, risk layers to compute that. So because I'm out of time, I'm going to skip a little bit and just say that current shoreline change research is focused on on algorithm development for rapid and accurate shoreline detection from satellites, which is another thing that we're doing to update the shoreline change rates across the North Slope Borough. So we're working on algorithms to get it from satellite derived images, and then these maps that we're talking about, we're going to have these sets out and available to the users by October next year. This for our first 3 pilot site communities is the intention, and then we'll continue with more communities from there. Thank you.